One topic students typically find difficult is exponential growth and decay, or applications. So exponential functions arise whenever a quantity grows, okay, so we can get growth, that's this, or decays, that's this, at a rate proportional to its current value. Exponential and logarithmic functions are used to model many physical occurrences. For example, population growth is exponential, or often is, can be decay though. Bacterial decay, calculating compound interest, radioactive decay or half-life, cell growth, bit topical, virus spread, okay, is exponential or growth or decay. And the law of exponential growth can be written differently. There's many different ways of doing this, but one of the most common ways is to write it like this. A of t equals a naught e to the kt. So a of t is the quantity at time t, a0 expresses the initial quantity, and k is the growth constant. Okay. Now, we get exponential growth when the k value, this k value here, is larger than 0, and exponential decay when k is less than 0. And the reason for that is, again, consider the basic function f of x equals e to the x. All right, that is this. But if g of x equals f negative x, then we get e to the negative x, which is a reflection in the y-axis. So when this is negative, here it's -1, here it's +1, so +1 we get growth, -1 we get decay. All right, let's see how some of the questions work. Okay, after 1,000 years, a sample of radium-226 has decayed by 37% of its original mass. Given the rule for the amount of radium-226 can be modelled by, so they've given us the way they want the function modelled is this form here. Show that the k value is this amount here, okay? And again, that is actually a negative number, okay? And I'll explain why in a sec. So let's just get the k value first of all. So what we know is that 37% of its original mass means that it's 63% left over. Okay, now that means that it starts with 1 unit, and that unit after a certain amount of time goes down to 0.63 of a unit because it's 37% less. So one of the really difficult things here is that students say that they don't know what the initial value is, okay? But what we do is we just say that the initial value in this case is 1 unit, which goes down to 0.63, okay? So here it goes. What we'll do is say that AN, the amount left over, is 0.63 equals the initial value, A0, which is 1, times e to the k, and time is 1,000. All right, so now what we'll do is we need to work out what the k value is. Okay, so I'm going to divide by 1, which is 0.63 equals e to the 1,000k. All right, now I need to solve for k, so I need to get it out of the exponent, which means we're going to switch to log form, which, hint, hint. All right, so what we're going to do is rewrite this as log e, and so that's the base, 0.63 equals 1,000k. Therefore, k equals 1 over 1,000 multiplied by log e 0.63 as required. All right, so now what we're going to do is find the half-life of radium. Okay, so what is the half-life of radium? State the value correct to the nearest year. So the first thing we'll do is write out our function. So a of t equals a naught, which is going to be 1, times e to the k, we've just found out, is 1 over 1,000 log e 0.63 times t. So this is how we're going to find out half-life, okay, is by using this formula here. And it's going to be when 1 becomes 0.5. probably didn't need to rewrite all of this. I could have just said 0.5 equals A of t. But now I'm committed. All right, so what we're going to do is solve this thing here. Now, first of all, I know that k is a negative number. Now, why do I know that? Because I know this is decay. So I know that this k value, this coefficient of t here, has to be negative for the graph to go like this. But also, every time you log a number between 0 and 1, the answer is always going to be negative. Now, what I'll do is I'll just explain why. So just say I was logging e to the, let's not go e. I'm just trying to think of an example here. Log 2, yeah, let's do that. Log 2 half. Now, this is a negative number, all right? Now, how do I know that? Log 2, I'm going to rewrite this as 2 to the negative 1. Grab that and stick it out the front. Negative 1 log 2, 2, which is 1. So this is, in fact, equal to negative 1. All right. So basically the rule is, because you can rewrite any fraction or any amount between 0 and 1 here with a negative index, you grab that negative index and stick it out the front. That means it negates this thing here. So it's always going to be negative. All right, now going back to this, what we want to do is run a solve on that. So we're going to go solve 0.5 equals 1 times, don't really need to put that 1. Now capital E for e to the 1 over 1000 times log e 0.63. I think that's it. Times t for t, please. All right, and state the value correct to the nearest year. So the half-life is t equals 1500.2. Therefore, 1500 years is the half-life. Okay. Now, with these solves here, just watch out for your brackets and all those sorts of things, and it might be appropriate to use the templates in Palette to try and make sure that you've got the kind of e to the, and it's all to the power of this rather than t slips out onto the other side of the brackets. What would this do to the answer? Completely mess it up, obviously. That means the half-life is t equals 0.5. So yeah, just really watch your brackets usage here. Okay, let's go another question. Show that k is equal to this value here if the growth of bacteria can be modeled by this rule. All right. So now you're getting us to use base 2, which is fine. They can choose any rule they want, and if they don't choose a rule, then you can use the general rule. A of t equals a naught times e to the kt. But because they want this one used, we're going to use this rule. So there are 4,000 initially, which grow to this amount here after 6 hours. So what we've got is growth, okay, which means that this value here, log 2, 200, that's going to be positive. So the k value is positive, as it should be. All right, so this is the initial. So we do have an initial specifically put down, which is 4,000, grows to 800,000 times 2 to the k and time in minutes, and it's 6 hours. Bit cheeky, 360 k. All right. Now what we'll do is slash off 1,000, and then 4 goes into that 200 times equals 2 to the 360k. Let's switch to log form. Log 2 200 equals 360k. Divide both sides by 360, and we've got k equals log 2 200 over 360 as required. Right, and then the rule, they don't want us to use it, but the rule an equals, what is it, 4,000 times 2 to the, and our k value, we know that now, is this value here, log 200 over 360 times t. Okay, and again, just make sure that this thing here, it's very clear that this is to the power of. Okay. An old question here from my notes back when I was at Sacré-Cœur. A certain Sacré-Cœur staff member is well known for leaving food in the refrigerator long after its use-by date. The biology teachers measure the initial amount of bacteria as 100 in the food. This particular type of bacteria will double in population every 6.5 hours. Okay, the number of bacteria can be modelled by this. Okay, show that K is this. 3 marks. So we're going to have to work hard for the K value here. And this came off, I wrote this question, it came off the 1-2 methods exam. I think it was the end of year exam. All right. So where to start? Well, we've got the initial amount is 100. So A naught is 100. So we'll go 100 times 10 to the. Now the K value is what we want to find out. T is time at 6.5 hours. Now because there's no decimal in this, we're going to rewrite that as 6.5, which is 13 on 2. So 13 on 2. So excuse the kind of algebra there, that 13 should be on the other side there, but that's all right for an intermediary step. And what I know is it doubles every this time period. So this 100 will become 200. Okay, so what we'll do is write 2 equals, so I'm going to divide both sides by 100, 10 to the 13k on 2. All right, what do we want to do next? Well, I think it's time to go to log form. So we're going to write log 10 2 equals 13k on 2. And now we're going to multiply this by 2. Oh, yeah, this is hard. Right, so we're going to get 2 log 10 2 equals 13k. Now I'm just looking at what I have to show, and what I have to show is log 10 4. And what's happened here is that I've gone, okay, so that 2 there needs to be brought up here. So it's kind of like simplifying in reverse. We're going to rewrite this as log 10 2 to the 2 equals 13k. So instead of going out the front, we're going to bring it up there, which then produces log 10 4 equals 13k, k equals log 10 4 over 13 as required. Tough one there, 3 marks. In this example, we've got a radioactive substance decaying in a laboratory. So what I know is we're going to get this kind of an arrangement here. Initially 5 kilograms of the radioactive substance was present, and 4 days, that's T, half of it remained. The mass R kilograms of radioactive substance at time T days after it was placed in the lab can be modelled by this. So they're telling us to use this version of the formula. So state the value of R0, that's initial, that's 5 kg. Show that the value of K is this. Okay, so what we're going to do is say that 5 times e to the, and that's going to equal, now initially there was 5, and 4 days later half of it remains, so that's going to be 2.5 e to the, now it's negative kt, so it's 4 days where t is time in days, so we're going to go negative 4k, and what we've got to do is find or solve this for k. So what we'll do is divide by 5. Now what we're going to do, 2.5 over 5 is a half, so we're going to write that as a half. Just having a sneak peek at the form. So let's go to log form. Log e half equals, what does it equal? Negative 4k. This needs to be 2, so we're going to grab this 2 and chuck it in the numerator and write it as a negative index. Log e 2 to the negative 1 equals negative 4k. that negative one's going to go out the front. Negative log E2 equals negative 4k. Now we're going to divide both of it by 4, and since that's a 1 out the front of the log, it's going to be k equals a quarter log E2 as required. Right, sketch the graph. Well, don't know how much detail to go into really, but I know it's decay, so knock together your axes like so. We've got, what are the variables? Time, I presume, and R. The initial amount is going to be 5, and it's going to sweep down like this and asymptote along here. So I'm only going to draw this part of it. And let's draw an asymptote along here at equals 0. And the reason I didn't continue it along there is because you can't have negative time. Okay, so 0, 5, and there's my sketch. To the nearest hour, how long after it was placed in the lab had 80% of the substance decayed? Alright, so what we're going to do is, so 80% of the substance decayed means 20% of it left. So let's work out what 20% of the initial amount is, which is 5. So the way we're going to do that is go 0.2 times 5 is 1. Okay, so what we're going to do is say when the 5 becomes 1, can you tell me how long that will take to happen? So it's going to be e to the kt, so I'm just using again this model here. So k is this one here, so it's going to be negative a quarter log E2 t. So we're going to solve this thing here. Alright, so let's jump on to Mathematica and start the solve. Solve 1 equals 5 times e to the power of negative a quarter times log, my base is E2 times t, and nearly forgot the double equals for t. Alright, so it's given us the complex solutions. Don't know why it hasn't defaulted to reals. That's better. Alright, so t equals 9.28771 dot 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 dot. So to the nearest hour. Okay, so because it decays at 9 hours, it wouldn't have gone under. So we need to say therefore 10 hours. Okay, so it's going to be, if I say, if I round to 9, what's going to happen is 80% of the substance hasn't decayed yet. I might actually show you that with Mathematica. So I'm going to grab this part here, Control C, Control V, and I'm going to put 9 in and calculate that. Give us a numerical. That's not what I wanted. No, that's exactly what I wanted. So at 9 hours, there's still more than 80% of it left. This question wants 80%, so it needs to be below 1. So if I replace it with 10, what I'd be willing to bet is that this value here comes out below 1. There it is, 0.88. So it's going to be 10 hours. Alright, the number of parts per million of E. coli in a stream T hours after a pollutant containing E. coli are introduced is modelled by this. Okay, how many parts per million are there of E. coli introduced in the stream? So that's at that's going to be x of 0. So at time 0, how many are introduced? And what's happening? Like, so what do we got? We got a log function, and it's been translated e to the 2, so roughly 9 units to the left. So this is going to be like something like this, right? And it wouldn't be this. Well, we're going to sketch the graph here, but I still kind of prefer to do it straight away. So it's going to be x of 0 equals log e squared, which is equal to 2 log e. That's a weird looking e. Not happy with that. Equals 2. So how many parts per million? It's 2 parts per million. To the nearest tenth of a part per million, how many parts per million of E. coli are in the stream at t equals 10? Okay, so we're going to go x of 10 equals log e 10 plus e to the 2. Just seeing if we can, I mean, that's the answer, but they want it to the nearest tenth, so let's use the calculator to do this. So I'm going to go log e 10 plus e squared, please. Gives numerical of that. So that's 2.85. So 2.855 dot dot dot. Therefore 2.9 parts per million. Sketch the graph of x against t. All right, so we know that the basic log graph, so y equals log e x, is going to look like that, asymptote here. So this one is, as I stated, shifted e squared to the left, which means that this is asymptote moves roughly, so e is 2.7, so let's go roughly 3 squared is roughly 9, so it moves roughly 9 units to the left. So the y-intercept is going to be 2, okay, and what it would do is come up through the y-intercept like so, pick up around about here, then continue off in this direction here. So we're going to say 0, 2. This is t, this is x of t, and that'll do for a sketch. Don't need to put the asymptote in really because it's out of domain. Okay, to the nearest hour, how long after E. coli is introduced into the stream are there 4 parts per million? Okay, so what we're going to do is say x of t equals 4. Let's go ahead and solve that thing. So we'll go solve 4 equals, what's my function? Log e base and t plus e squared. And can you solve that for t, please? Yeah, sounds good. Okay, so hours. So t equals 47.2091 dot dot dot. Okay, so to the nearest hour, after how long is E. coli? Are there 4 parts per million? Okay, so what do I do? So the answer is going to be either 47 hours or 48 hours. Okay, now what's happening is the amount of E. coli is growing. Okay, so if I go down to 47, all right, there's not going to be 4 parts per million. So the answer is going to be 48 hours. Okay, and again, what you should feel comfortable doing is just checking that. So I'm just going to grab this and just try it again, just to make sure I've done this correctly. So I'm going to use t as 47, and again, what I'm thinking here is that this will be less than 4. It'll be like 3.9. There you go. All right, so that means that the 48 one gets us over 4 parts per million. Alrighty, and the last question. So assuming that population growth is exponential, the population of Deer Park was 10,000 at the beginning of 2004 and 17,000 at the end of 2015. Find the population at the end of 2017. What year will the population be double? Write your answer to the nearest 1,000 people. Okay, so what are we going to do with this one here? Okay, so I think we'll just use our own version of the formula. So A of t equals A naught times e to the kt, because it doesn't suggest a model. So the initial amount is 10,000, which grows to 17,000 at the end of 2015. Okay, so what we'll do is we'll say 17,000 equals 10,000 times e to the, now we need time, so this is over how many years? At the beginning of 2004, so 2004 to 2014 is 10 whole years, and then so that'd be 2004 is 1 year, 2005 is 2 years. Oh my god, I can't believe I'm doing this. So that means, so each instance counts as 1. So that's 2014 will be the 10th, 2015 will be the 11th. So this is after 11 years. Okay, so 2004 counts as 1 year, and 2015, or the end of 2015, will be 1 full year. Is that right? Let me think about that. Yeah, happy with that. So let's run with it. So it's going to be t is 11k. Right, so as we've been doing, what we'll do is find the k value first of all. And the way we'll do that is by 3 chopping off zeros. 1.7 equals e to the 11k. Log form, log e 1.7 equals 11k. K equals 1/11 times log e 1.7. Okay, so this value here is positive, so we can tell that that is growth, which is what's happening. Okay, so let's write our formula. A of t equals 10,000 times e to the 1/11 log e 1.7 t. All right. Okay, so find the population at the end of 2017. All right, well, let's use a function here. A t equals nearly. Times t. I like to have a little bit of a look-see at the graph. Yeah, sort of makes sense. Let's go and shrink the domain a bit. 0 to, let's go 30 years maybe. Okay, so yeah, sort of got this exponential growth, which makes sense. All right. So, okay, in what year will the population... No, find the population at the end of 2017. So at the end of 2015, it was... What was it? 17,000? In fact, let's try that out. A of 11. we're going to stick 11 into the function, and it says 17,000. That's a good sign. So end of 2017 is 2 years after that, so it's going to be A of 13. Write your answer to the nearest 1,000 people. Okay, so we're going to do A of 13 equals 18721.8. That'll be dot, dot, dot. To the nearest 1,000 people means round to the nearest, so tens, hundreds, thousands. Therefore, we're going to say 18,007. Is that rounded to the nearest 100? Units, tens, hundreds, thousands. Okay. Let's try that again. Alright, so that's rounded now to the nearest 1,000 people. Can't believe I nearly did that. Okay, now, in what year will the population be double that of 2015? And this is not going to be to the nearest 1,000 people. This is going to be to the, well, in what year? Okay, so what we'll do for this one is say A of t equals, so double that of 2015. So 2015 is 17,000. So we want 2 lots of 17,000, which is 34,000. Okay, let's go over here. So we'll go a solve. A of t, 34,000 for t. Now I wonder whether it's going to give me complex. It's not. Okay, so t equals 25.369 dot 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 dot. Okay, so this means that, okay, in what year will it be double? So that's going to be somewhere within the 25th year. Okay, so somewhere within that year, it's going to be double. So what is the 25th? So 11 years is 2015. So 2025 is going to be another 10 years after that. So that's 21. So 2026 is 22, 23, 24, 25, 26. So that's 27, 28, 29. So 25. So it's somewhere within the year 2029. So therefore, somewhere within 2029, the population will reach, what did we say it was? 34,000 people. All right, prefer not to work in years. I find that really difficult, obviously. All right, so there is the exercise. Good luck with that.